Good morning, and I welcome you all for today's webinar, which is our third webinar of this series. I also would like to welcome on behalf of Industron and Bruker. My name is Pratyang Rastogi, and I will be your host today. So in today's webinar, we'll be discussing basically on in situ nanomechanical testing techniques and property mapping. In situ nanomechanical testing is basically the integration of our nanomechanical testing capability along with the imaging, high resolution imaging capabilities of scanning electron microscope or transmission electron microscope. Dr. Asif will be discussing more in detail about the concepts and how it is essential in today's particular field. So I would like to also mention before going forward that all participants are in listen mode only, and we will certainly take all the questions at the end of the talk. Please drop your questions in Q&A tab during the discussion, during the talk. And should you face any problem in joining or audio related issues, please drop me a message. And without further ado, I would like to introduce Dr. Asif, who will be giving today's talk. He's currently Managing Director of Industron Nanotechnology Private Limited, also heading the R&D division. He's graduated from University of Oxford with the PhD degree in material science in the year 1996. And also he did his master's in mechanical engineering from Indian Institute of Science. So he has 30 plus years of experience in designing and developing nanomechanical test instruments. And he has been the key player in developing these nanomechanical test instruments at Bruker Nanosurface. He has over 120 publications and 22 active patents. He has also won 400 R&D awards. So without further delay, I would like to invite Dr. Asif and deliver today's lecture.
Okay, thank you, Pratyang. I think hopefully he can hear me.
Yeah.
If you can hear me, just say yes.
Yeah.
And I'm going to share my screen, and you can see my screen as well, right?
Yeah, we are seeing this. Yeah, we are seeing the slideshow now. Okay,
very good. So welcome everyone for this webinar. This is the third part of the webinar. And in today's webinar, I will be talking about more on the in situ nanomechanical testing. And I think Pratyang displayed some videos. It's pretty much, that's what I'm going to cover in this talk. So I think it's better to kind of go through what we did in the last two webinars. I introduced the concept of nanomechanical testing by doing a depth sensing inundation technique where you use a rigid probe, apply a stress onto the sample, and then measure the load displacement response. And we can deconvolute the mechanical properties from this load displacement curve. That is the fundamental that we covered in the first webinar. And then in the second webinar, we also looked at different types of the response that you will get from different materials, elastoplastic. In the last webinar, we saw the viscoelastic response of polymer materials, and I also introduced a different concept of measuring properties through stiffness measurement technique, where you apply a sinusoidal force, modulated force, and measure the sinusoidal displacement response. And from known force and the displacement response, we can calculate the stiffness of interaction when you are in contact with the sample. And from that, we can deconvolute properties like hardness and modulus. That is what we discussed in the last meeting, right? So by now, you probably be very familiar with these low displacement curves. And they come in different shape and characters. And that's why we call it as mechanical fingerprint. And it kind of tells you what happens underneath the indenter and what kind of different mechanism is leading to this kind of low displacement behavior. Okay, So, for example, polymer material, last time we covered about the viscoelastic response, creep response, and the loss of energy due to viscoelastic property, right? The loss in storage modulus. Okay. So this today, what I'm going to talk about is a unique response that you measure when you do on certain material. For example, if you take a well annealed single crystal tungsten sample and it's electropolished single crystal tungsten sample, and if you do an indent on that, and if you do up to some load, like in this case about a millinewton, and then load and unload, the response that you will measure is totally elastic, right? So you load and unload, it retraces its own curve, and you see that kind of a response. And if you apply a little bit higher load, you can see a sudden jump in this load displacement curve, which we call it as pop. And so it's not a continuous, smooth, nice curve that you have seen before. It is kind of a jump. You can see as jump in the load displacement curve. And there is a reason why there is a jump. And that was kind of a subject to a lot of research at the point of time that when I started doing my PhD work at Oxford. So I'm going to take you back to 1993, 94. At that time, in nanoindentation was very, very starting basically at started infancy. And we were trying to understand what's going on when we try to do this kind of experiments. And Professor Pithika, Sir John Pithika at Oxford and Warren Oliver, they observed this huge pop in electropolished single crystal tungsten, and we were trying to figure out why you have this jump in the load displacement curve. So I took it as my PhD problem, and like in the last webinar, I introduced you to do this dynamic measurement by modulating the force and measuring the displacement response. So I was kind of learning at that time how to do this and the instrumentation aspect of it, and how I can apply this concept in a different format when we do this kind of experiment. So that is the kind of timeline I was in at that time, and then I was trying to use that technique to understand what's going on. So. So the important part is basically if you take this material and if you do and if you try to measure the stress at elastic contact, they're pretty huge. They almost goes to the theoretical strength of the material. And if you look at after the popping, if you try to go and measure the hardness or the mean contact stress, it drops down. So it goes from very high theoretical strengths to lower stress when you have this popping. So we kind of at that time recognized that this could be a reason. The reason could be that you have materials where you have very low dislocation density. So you are actually almost probing the theoretical strength of the material. And then when you reach some critical stress, you nucleate this dislocation, and the dislocation multiply and they move. And that's why you see this popping. If that theory is right, that hypothesis is correct, then the technique that I introduced last time in the webinar, that is the measuring the stiffness as a function of time for creep measurement, that will be a kind of a technique that we can use. For example, what we can do is we can I'm going to go to this. We can load and hold the load constant and kind of observe what happens to the stiffness as a function of time. Okay. And if there is a creep, for example, the creep means if you have a dislocation, and if the dislocations are mobile, it will lead to a kind of a creep, right? So that you can observe if you observe the stiffness as a function of time. So when we did that at elastic contact, you could see in this curve that you don't see any creep. It is pretty much flat. Nothing happens, right? And that kind of tells that there's no dislocation motion, and the stresses that you measure is the theoretical strength of the material. This is kind of indirect observation. If you compare after the popping, I'm going to compare here. You can see this in this slide. This is before popping. You load up to maximum load and measure the stiffness as a function of time. Nothing happens. There's no creep. Nothing happens. But as soon as there is a popping, you can see that during popping, there's a huge jump in the stiffness. And then when you hold, you can see the stiffness is increasing as a function of time. That kind of tells there is a creep, there is a time-dependent plastic deformation, and that happens only after the popping. So by this indirect observation, I was able to tell that this popping is mainly due to dislocation nucleation and multiplication, and it nothing else. And there was other theories at that time that this sudden jump is maybe due to oxide layer breakage. Any material, any metals if you take, there is a native oxide, right? So if the oxide layer breaks, and that we can also observe as it's jump in the low displacement curve. But in our case, that we were able to prove that this popping is mainly due to dislocation nucleation. So at the same time, we were trying to prove this by other means, that is by doing experiments inside a transmission electron microscope. So we didn't have that equipment at that time, so we were planning to build at Oxford. I did apply for a Royal Society fellowship and we was waiting for the fund, but that fund didn't come. I wanted to finish my PhD work, and then I finished. I moved to US and joined as a postdoc at Naval Lab. I worked there for 3 years, but this problem was back in my mind for a very long time. So then when I joined Hydrotron, Hydrotron is a kind of a private company, and to investigate this kind of theoretical concept, almost like theoretical concept, it's kind of risky for a private company. So I have a story that I would like to tell you here. This is also kind of a story why I push for collaboration. So when I was giving a presentation at a conference in Phoenix, Arizona, I believe it is an ASME conference, I met Eric Stark, who at that time was working at National Center for Electron Microscopy, and he presented a paper on doing in situ inundation, where he was showing how the grain growth happens and this and that. But at that time, in that setup that he had, he didn't have any way of measuring the stresses or strain in terms of low displacement curves. So I went to him and then said, we know how to do this at Hydrotron. Would you like to collaborate? So he visited Hydrotron. So we worked out, and then we applied for a grant here in US. There's a nice program called SDAR. We applied that grant. We got the money. That helped us to build this instrument. That is the background story. Where this particular holder, what we did was we had elements that we already used in our instrumentation, these piezo tubes that we had for scanning probe microscopy, the transducer that we had, 3-plate capacitance transducer, we kind of put together inside a holder that goes inside the transmission electron microscope. And this is the team, you can see Andy Miner, who was a student at that time with Eric Stack, Pauline Warren, myself, and Edward. Edward is a kind of a magician who built all this transducer by his hand. And so as a team, we worked on this work. And so the very first experiment, as you expect, I was trying to do was to understand when you bring two materials closer together, what happens, and if you have stresses, if you have a system where the dislocation density is less, and the stresses can reach us to theoretical stress, can you see this dislocation nucleation? This is the first thing that I want to do. So that is what we end up doing very first few experiments inside the TEM. Okay, so by then, like in 6 years, there were a lot of observations. So we were kind of looking for what material to test inside the TEM. Tungsten is not a good material, so we end up using aluminum. Aluminum is very good and it is electron transparent. So, but to do that, what you need to do is you need to deposit on a wedge so that it is electron transparent. You can see there is a silicon wedge, and on top of it, you have an aluminum deposit. Basically, it's a kind of an electron transparent film. So electron can pass through and then gives you an image. From the side, you can apply the load, and there is an indenter will come and make contact. This is what I'm going to show you in my video next. Here you can see this. There is an indenter, and this is a aluminum grain, dislocation free, and bring the tip, make contact, boom, you can see the machine work. But you could see that at the initial contact, small contact, he started to nucleate these dislocations. And each jumps that here, this is a huge load drop. You could see this dislocation nucleation and multiplication. So it kind of gave us that direct proof. Whenever you see this kind of a jumps in the low displacement curve, we were able to correlate that with dislocation, nucleation, and multiplication. So yeah, that's something that I started a long time ago. I was able to see that, I was very happy. And we were able to also kind of realize when you do this, for example, when you bring two materials closer to each other, and I'm going to play this video also, and I'm going to explain this data. So you watch this video, the tip is approaching to the sample surface, and then immediately start to see this dislocation nucleation. Okay. On this side, if you look at this this curve, you can see that as the tip is approaching towards the sample surface, this is where it is coming. At some point, it is making contact. That's why you start with this develop stress, and that stress is nucleating these dislocations. But then you can see a huge oscillations. But if you observe this, you can see that if this is the zero datum, and below that, for example, if the tip is getting pulled towards the sample, it is a negative force, which means it is an attractive interaction. As soon as the tip contacts the sample surface, you will start to see the repulsive forces. But in this curve, we can see that most of it goes to repulsive and then attractive, repulsive, and attractive. That kind of tells you something is happening. What is happening over here is, unlike in tungsten, here there is an oxylayer breakage. But at the same time, you are exposing the native aluminum, virgin aluminum, which has higher surface energy. So the tip is getting pulled towards the aluminum more and more. That's why you have this attractive interaction. Okay. But the whole point is like, even within this attractive interaction, without getting into the repulsive interaction normally that we will have for inundation, you can see the stresses are very high, and the stresses are good enough to induce dislocation nucleations. This we were able to see that directly and correlate that with the low displacement response or the approach curves that we got in the TEM. So kind of solved some of these things that we were guessing at that time. Okay, and it also kind of gave a clear picture that even surface stresses, surface forces are good enough to cause this dislocation nucleation. So that work that my push was to understand what's happening in this low displacement response. That's why I went and built this the holder. But then it helped us to do this mechanical experiment inside the TEM. We took a bigger challenge. Doing these experiments inside the TEM is much more challenging than doing inside a SEM, because SEM you have much more room. In TEM you have 4 pieces with a gap of over 2 to 5 millimeter. And within that gap, you need to put this transducer and do all of that. It was a very tough task, but we were able to do that. I'm talking about year 2003, 2004. We built holders that can go into FEI or Hitachi or Geo microscopes. And then we also then realized that this is a nice way of studying the mechanical response inside the inside the electron microscope. And so because we are able to see and we don't need to guess, we were able to measure the stresses and we were able to see what's happening to the material. So that's why we came up with this slogan, seeing is believing. And then we applied this same technique to SEM. And then later on, after 10 years that we wanted to work with the biological community, we put that on a biological microscope. That's why we have all this instrument now available on microscopes where we can do this in situ experiments. Okay, so now not Pratyang, is that everything all right? Okay. So now here another example I would like to give is a compression experiment. So this is around 2004, 2005. There were a lot of groups who were working on small pillars, and particularly at the Air Force Research Lab, Mike Yuchik was doing experiments on pillars, and he was able to see that as you reduce the size of these pillars, the strength of these pillars goes up. It is against our common, the way we learn metallurgy is basically The yield stress is scale independent, and even if you reduce the size of this material, you should measure the same yield stress, which kind of are not true now. We know that. And so there were a lot of theories why the strength of material goes up as it changes in the length scale. When it becomes smaller, why there were a lot of theories at that time. So we thought we may be able to look into this problem. So our postdoc, Z.V. Shan, he was able to fib this nickel pillars. And when you do the fibbing, what happens is the fibbing process introduces a lot of dislocation. Towards the skin, most of those dislocations will be toward the surface, closer to the surface. That's why you see this. This is a pillar, nickel pillar. There's a lot of dislocation. That's why it looks black. And here is a flat tip. I'm going to go and compress that pillar. And then you can see that as you compress, all these dislocations are moving to the surface and they disappear. So at the same time, when we were able to measure this stress strain response, the strength was going up and up as we compress. This is against like annealing, because in annealing, it is against work hardening, because when you apply stress onto a material and you generate more dislocation, the material becomes work hardened. But in this particular case, all those dislocations were there already. They're kind of moving towards the surface and they disappear, and the pillar becomes stronger and stronger. So Nix at that time at Stanford, he came up with this thing and he explained it beautifully with these results. The reason why the strength goes up is mainly because the dislocations have a characteristic distance that they have to move before they multiply, right? So for example, in this pillar, this is about 100 nanometers. So when the dislocation move, if they go to the surface and disappear, they're not going to multiply. So all the dislocation, what's happening, they move, but they move out of the system and they go to the surface, create surface step, and they don't multiply. So that's why this material is getting harder and harder and becomes less dislocation. You have just asked all the dislocations, so it becomes harder and harder. So we were able to explain that by doing experiment inside the TEM. Another example, for example, this is a spherical particles. This is a shell. It is a hollow particle. You can see a shell here, and it's mainly at that time it was cadmium sulfide, and we were trying to figure out, can we measure properties of these small structures? This is, in this case, is about 100 nanometers, 200 nanometer diameter spherical shell. You can see that you can apply the stress and break it. At the same time, you will be able to measure the low displacement and stress strain response. And after it breaks, we can also go into a postmortem analysis and see what type of fracture happens. So even small structures, nanostructures, we were able to compress or do some kind of a deformation inside the TEM and get some decent stress strain response, and able to say and model what type of deformation behavior it is. And so it was very helpful in that time. So I'm going to speed up. This is another example for silicon, but I'm going to skip that. So not only doing in addition, I mentioned that we can do compression, we can do tensile. To do the tensile experiment, we developed a device, we call it push-to-pull device. The reason is because the actuator that we had, it can apply linear load in one direction, right? So either we can pull up or push. Pushing is used for compression. We thought maybe a good idea that we develop a device so that you apply a pushing action, it kind of creates a pulling action. For example, in this particular device, this is the mobile part and this is a fixed part. In this gap, if you put a sample and if you push it, it is going to apply a tensile stress onto the sample. So that way you can do a controlled tensile experiment if you can fix the sample in between this gap. These gaps are generally about 2.5 micron. So that's what I'm going to show in the next video. And you can see that there is a nano wire has been platinum welded in the gap. And you can apply the stress and you can measure the response. And you can also see the video of the deformation behavior. You can see the dislocation nucleation and propagations and then the necking and then the deformation pretty nicely in these videos. Okay, so we were able to get this stress strain response. At the same time, we were able to observe that. Again, another video here. Here you can see this dislocation, how fast they are moving, and see that out, right? So I'm just showing these videos. They are pretty cool to see, and we can each jumps here is a response to the dislocation motion here. What you see on this pillar. Again, you can do, instead of a pillar, I mean, instead of a wire, we can also put a thin film, and then you can do this tensile test and get this low displacement response. Okay? And this is for a zinc oxide piezoelectric wire. And in this particular experiment, not only you can apply stress and understand the mechanical response, you can also measure the electrical response. This is a 4-point contact probe measurements. You can see there are 4 points. You can make a contact, apply a voltage, measure the current, so that you can measure the resistance as you pull. And this is for a zinc oxide nanowire. So we can do this in situ in real time. Okay, this is for a copper thin film. Here, a modulated force has been applied. You can see that sinusoidal force, and then you can start to observe. For example, it's kind of a slow cycle fatigue experiment, and you can introduce a small crack, and then you can watch how the crack is growing as you apply this stress, and you can see this. You can do dynamic loading as well as you can do static loading, where in between you can also observe how the length of this crack is changing as you apply the stress, and you can observe the arc curve behavior. Okay, I'm going to skip that as well. So along with that, like if the tensile or compression or fatigue type experiment, we thought, why can't we help the tribology community? Can we do some neat sliding experiment inside a TEM? And because tribology is kind of such a complex deformation phenomenon, anything by observing in TEM will help us to understand this. So I don't understand this sample. This is a kind of a geological sample. It comes from earth mantle. This is called olivine. And for some reason, the University of Minnesota team was interested in understanding the deformation behavior, and they wanted to understand the friction behavior. So we were able to put that inside the TEM, and you can see this sliding response. You can, in this particular case, not only you can measure the normal force, we can also measure the lateral force, so that we can kind of build how the friction is changing as you slide. And if you apply higher forces, you can start to see that the band formation underneath. It's kind of this, I don't know whether it is adiabatic shear bands or just the shear bands underneath the sample as you slide. And at some point, they become hardened and they can come out from the surface in kind of a material removal mechanism. But in the whole process, we can kind of measure both the lateral and normal forces simultaneously and have some kind of an idea about the tribology. This is kind of in the beginning. I think we haven't done much, and I haven't seen anybody tribologists jumping onto this. But this whole thing is open, and we can do a pretty neat tribological experiment inside the TEM and understand the fundamentals of tribology by doing this way. Okay. So now, right now, like I'm going to jump into SEM. And in the TEM, we can go do some fundamental research and understanding the deformation mechanics and how the dislocation nucleates or fracture initiate or phase transformation happens. All those kind of fundamental things that we can go and observe. But in a practical sense, like if you wanted to understand the fracture behavior for a bigger sample, we like to do it inside a scanning electron microscope, so that's why we built this holder that goes inside a scanning electron microscope. And these holders, this is the latest one, which is PA89, which has encoded stages, which has about 1 nanometer resolutions. They can move about 20, 30 millimeters with 1 nanometer resolution. It's a robust design and a higher effective stiffness, so we can go for higher loads and higher. The earlier designs had load limitations. Now we can go up to 3 meter load and apply that stress onto the sample. And you can also have this modular concept where you can go change the load cell if you want. And on the stage side, along with these linear XY stages, You can also have these rotary stages, and these rotary stages we can have rotation or tilt in a combination. I'm going to show that video again so you will understand what I'm talking about. They can move in either in this direction or along the axis of the transducer. So for example, the rotation in this case, the configuration A, the whole thing rotates in this direction, whereas the tilt is in this direction. Okay, so and the point is basically when you have these 5 degrees of motion stages inside ACM, ACM has a lot of detectors, like EBSD detectors, and they are in different locations. So here we can come and do a mechanical test. And then if you want to go back to see what happens, for example, crystallography, how the grain has elongated or not, you can go to EBSD detector and do an EBSD mapping and then see how the grain has, or you can see the grain orientation and bring it back and do a mechanical test with this indenter. So that's why this 5 degrees of freedom is very useful. This is what I mentioned, that you can see the tilt action here. Okay, and then it's kind of moving in this direction. In this case, it is going to rotate. So with this combination, what is it used for is to understand the anisotropic behavior. For example, if you take calcite sample and if you rotate it at different orientation, you will have a different kind of a response because of its crystallographic orientation, right? So if you want to understand the anisotropic behavior, this rotary stage is very useful. Okay, again, these experiments we can do at room temperature, at higher temperature, as high as about 800 degrees C. I believe this 1000 degrees C is available now, and you can do accelerated property mapping. I think I covered this in the last webinar, where we can do array of indent at faster rate, 5 indents per second, so that you can do like hundreds of indents in very few seconds, or maybe in 1 or 2 minutes you can do thousands of indents. So it's kind of for if you wanted to map the property over a surface area, if you have a two-phase material, it's very, very useful. And doing that inside the ACM is very useful because, for example, in ACM, you have this EBSD detector. You can go and map this crystallographic orientation, and then you can do this fast indent and then map the mechanical and then compare with the EBSD map with the mechanical property map. So I'm not going to do too much on this, but I'd like to show this video where you can see this indents being done very fast on a material. It's a multi-phase material. I think it is a high entropy ally, and after doing these indents at each point, you can measure what the property is, so you can get a property map, and then you can go to an ABSD detector and get the crystallographic orientation. In this particular case, this is for nickel-based superalloy, but for other materials, you can combine that with EBSD and understand what the crystallographic orientation means to mechanical response of the material. So you can do this cross-correlated microscopy as well as mechanical property correlation. Okay, this is a silica particle, and not only you can do combustion, but you can also do low cycle fatigue or dynamic load. You can see that this is a particle, and then with the electron beam, we start to oscillate. You can see the plasticity or the ductility of this particle, and we found that this ductility, enhanced ductility, mainly due to the electron beam. In fact, this glass silica particle can be plastically deformed to any shape with a high ductility if you use this technique. Okay, so again, if you have Kikuchi diffraction detector, we can do high resolution mapping, and we have adapter that allows you to do that. And with that, you can go and map this for different stresses. We can do high resolution crystallography mapping along with the stress and strain that you can apply, and you can directly correlate. So I'm not an expert on this, but if you want to have more information, you can reach out to us. We can link up with the right people. Okay. Again, you can do this nanotribology inside the ACM, where we can go, for example, this is a local dielectric material on a substrate, and the whole point is what is the adhesion strength of this film on the substrate. by doing a scratch experiment, we can kind of delaminate and then measure that. So we can see what type of cracks form. So I'm going to show this video again here. This is, first you apply the normal load and then do the lateral load. At some point, you're going to create the crack, and then you can kind of, you saw the delamination of the located dielectric at the same time. You also create a lot of cracks, and those things you can directly observe on this force versus displacement curve with both normal force and lateral force, and then you can kind of correlate at what force you have delaminated, and knowing the critical loads and the forces and then the dimensions of your indents, you're able to calculate what that is the strength of this liquid dielectric film is. Okay. So you can do one good thing with the SEM-based Institute of Mechanical Testing is now you can do these experiments up to 800 degrees C. So you can heat up a sample, heat up the tip. You have a heater here that heats the tip. You have a heater here that heats the sample, and you can go up to 800 degrees C. I believe you can go up to 1000 degrees C now, and measure the mechanical response of the material as a function of temperature. You can see the tip being heated here, okay? And this is the sample heater. And this particular video I'm going to show you, this is done at 1000 degrees C, and we figured out a way to image it without any thermo electron problems. The image is pretty nice, and you can also get this nice low displacement curve. And from that, you can do the stress strain response. And this is very useful mainly because it kind of not only measuring this response in terms of load or stress, directly observing what type of information is happening in real time, kind of understands to develop the deformation mechanics. I can kind of show you here. For example, if you do it at room temperature, you can see the shear bands, and that is totally different when you do it at 1000 degrees C. Okay, so you can have some kind of a direct understanding of the deformation mechanics along with the stress strain that you have to measure. This is for a silicon sample. We are working on this paper, so I'm not going to talk too much about it. We found something interesting where when you do indent on silicon at a different temperature, initially you see a high increase in hardness, and then eventually the hardness decreases. So this is mainly because of two competing mechanisms. One is being due to the phase transformation, another being due to dislocation based, because higher temperature can permit more of dislocation based deformation mechanics at room temperatures is more of kind of stress induced phase transformation based mechanics. Okay, so I think I pretty much covered most of what I wanted to cover. So I would like to kind of stop it over here and take any questions. This is kind of a summary slide where I'm kind of putting all the things that you can do. I forgot to mention about this kind of tensile test where we can fib a specimen like a dog bone shape, and you can also fib the tip like a grip. And if you want to do direct pull test, you can go and do this and measure the response. That is also possible. So even if you have a complex structure, you can apply and bring and apply, make this stress strain response on the video. So there's a lot of other possibilities that you can explore. This is for a multi-stack semiconductor material. This is a 3-point bend test. You can see there's a fracture happens as you apply the stress. And then depending upon the orientation where you apply the stress, the fracture pattern will be different. So all these things are possible now, and then we can really do this inside SEM and TEM. So with this, I'm going to stop and take any questions. And if you have, the next webinar, we'll be covering more on high temperature. So that's why I'm not going to cover much on this particular talk. And so with this, I'll stop over here. Over to you.
Yeah, sure. Thanks, Dr. Asif. So yeah, we are open for any questions if there's any from the audience. So far, we haven't received. Okay, we've got a question from Digvijay. is it possible to perform high strain rate like in the order of 1,000 to 100,000 per second deformation using this in situ holder?
Yeah, so you can do high standard experiment, but based on the bandwidth of the transducer, there are some limitations, like how fast you can do, what will be the highest strain rate, but you can do high strain rate experiments. I don't have the number right now, but if you're interested, you can contact me or Protian, we'll get back to you. It's going to be limited only by the bandwidth of the transducer. So we can do very high strain rate experiments inside a SEM. We have done that actually. I don't know the number yet, but upper limit I don't know. But we can do, I think, 10 to 3 easily, 10 to 4 maybe. I don't know about that. Okay.
Okay. Can I ask how to mount the sample onto the push to pull device?
Your break.
Can I? The question is
okay, so
on how to mount the sample onto the push to pull device.
Okay, so here is the push to pull device, and if you see here, there is a gap, and in this gap you bring whatever, if it is a thin film, you deposit the thin film on this device, so then you have something in between the gap. Or if it is a nano wire, you use inside the SEM, you have these manipulators that you can use to bring the nano wire and anchor it over here, and you do the platinum welding at both the end. Okay. So that kind of gives you a way to do this. I think I kind of shown that in the, maybe I'll get to that. In one particular case, we had one image. Maybe that was with the T. Yeah, it's here. You can see this is a platinum weld that anchors the specimen in the gap. That's how you fix that. Okay. Yeah. Hello.
I'm just seeing if there's any further question.
Okay.
No. Okay. Well, I think that's it. So I think, yeah, that's it. So I definitely would like to thank all our participants today for sparing time from their, from their schedule. And as mentioned, there is another upcoming webinar, which is also the last webinar of the series, where we'll be talking more on the tensile testing as well as high temperature applications. So please do register for that webinar. It's a separate link. So after registering, you will get a link to join, and that's happening on 17th of December. Till then, stay safe and yeah, take care. Have a great day then.
Thank you all. Thank you. Bye-bye.
Yeah.